Hi there. This is the third lecture on trustworthy AI. The topic for this lecture is adversarial examples. Adversarial examples are very important topics in the space of machine learning in general. But when we talk about trustworthy machine learning slash AI, adversarial examples stand out as one of the most important um, uh, things to study and to make sure that machine learning models are not vulnerable to adversarial examples. Okay, so in the scope of our trustworthy machine learning roadmap that we're going to follow throughout this course, where we are right now is the focus for this lecture is going to be on security and implications of security on safety. And specifically, we're going to talk about when models are going to be fooled using this phenomena called adversarial examples or adversarial inputs to machine learning models. So throughout the course, I'm going to flash this trustworthy AI/ML roadmap so that we have an idea of where we stand as far as the objective that we want to achieve in the sense of the broader goal of making machine learning trustworthy. Okay, so what are we going to do in this lecture? The first thing we're going to talk about is what are adversarial examples, why we should care about adversarial examples, and why do they exist in the first place? What are the root causes of adversarial examples, if there is any? Next, we're going to look at threat models and the different kinds of attack, adversarial example attacks that are out there. And given adversarial examples are classic security violation through, for example, if you look into intrusion detection and the use of machine learning in intrusion detection or malware detection, etc. This is a very natural thing. It's because it's an adversarial, it's a naturally adversarial domain. Okay, so we're going to talk about threat models and attack taxonomy. And after that, we're going to see how adversarial examples are crafted. So how do adversaries are going to generate adversarial examples from, let's say, clean inputs? Of course, once we talk about how this adversarial inputs are crafted or generated, we're going to also look at what are the mechanisms with which we're going to defend against adversarial examples. And at the end, we're going to step back and try to connect the phenomena of adversarial examples with this general notion of data distribution shift. Okay, so that's going to be our plan. All right, so starting with what adversarial examples are. So I have tried to define this broadly in the first lecture, but we're going to expand on that definition today. So adversarial examples are in the pipeline, the supervised machine learning pipeline that we talked about. I'm going to explain it a little bit here. So look at the adversary over here. The adversary here is trying to interact with a deployed machine learning model by perturbing or applying some transformation on a given input so that the input would be misclassified by the classifier. So the goal of adversarial examples is, at the end of the day, the adversary wants to evade or fool or bypass a certain checkpoint that is powered by a machine learning classifier. And this could also translate to causing harms or might have negative consequences that would potentially harm people. And I'll give you examples for, as to where this is possible. But in general, adversarial examples are defined as inputs to machine learning models that an attacker has intentionally crafted to make sure that the adversarial example fools the model or the model makes a mistake. So over here, what you see is for an input X, the adversary is going to add this perturbation delta. So this is what we call perturbation or adversarial perturbation, which for now you could perceive as just some manipulation of the input. Of course, this is not a random manipulation. It's a targeted manipulation where you want to make sure that you bypass the classifier while at the same time the perturbation is not very visible or it doesn't raise any red flags. And the ultimate goal is for the classifier to classify this as something else or different from the original class. Okay, so that's basically the meaning of adversarial examples and the adversarial goal that the adversary is trying to achieve through adversarial examples. Okay, so let me expand a little more on this notion of adversarial examples. So here is a slightly elaborated description that would make it a little formal. So what we're trying to do in adversarial examples is, given some machine learning model, let's call it F, that maps a set of inputs to an input in this data distribution X to an output Y, let's say a class. So this X is going to be mapped to a label Y. Let's call it Y true, or to mean that this is the true prediction or the true label of the input. Now, the idea, as I said earlier, is to generate X prime, which is X modified or manipulated with the adversarial perturbation. Okay, so an adversarial example is this X, the original X plus the delta or the perturbation. Now, so when this happens, we want to ensure that for the adversarial perturbation to be successful or for the adversarial example to fool the model, the function or the model, when it is queried on X prime, the adversarial example, should give us Y prime, and this Y prime should be different from the original label Y true. And the actual perturbation that we perform, delta, here is bounded by some notion of norm or distance by this upper bound called epsilon. And the epsilon here is what we call the perturbation budget, or the maximum allowable perturbation that you have to apply so that the misclassification happens while preserving what we call semantic integrity of the input. So semantic integrity here could mean many things depending on where you are or what domain this adversarial example is being generated in. In the image domain, for instance, a semantic integrity means the image, if you perturb an image of a dog, it should still look like a dog to a human, but the perturbations should be imperceptible, visually speaking, for a human, but somehow the classifier is sensitive to this perturbations. If you take an example in the malware domain, the semantic integrity has a slightly more constrained meaning here, where if you take a malware sample and that malware sample is perturbed and then misclassified as benign, which is basically successfully fooling the model, then we want to make sure that the perturbed version of the malware sample should maintain the malicious behavior of the malware. So if in the process of perturbing the sample, you end up messing up with the sample. For example, if you perturb a binary, let's say a Windows binary or an Android APK, then the resulting adversarial variant of that piece of software that is expected to be malicious, that behavior should be maintained. If the behavior is broken in the process of adversarial perturbation, then it's not really useful. Okay, so I hope that gives you a lot of sort of, let's say, a broader view of how this can be formalized for adversarial examples. Now, I'll give you some funny examples that appeared over the years as we look at adversarial example problems. Just to give you an idea of the context of the historical context to adversarial examples here, in adversarial examples were first popularized back in 2013 when people observed this intriguing property of neural networks, whereby neural networks were simply misclassifying inputs with very minimal perturbations. And this is specifically on in the image domain. But adversarial examples happened or studied well before 2013, because sometimes people just misunderstand that adversarial examples are like 10 or 11 years old. That's not the case. If you come from the security and privacy background, like I do, adversarial examples are there wherever there are adversaries. For example, if you're building an intrusion detection system or a malware classification model, then you anticipate clever adversaries who would try to bypass that model. So here is the classic example of a panda misclassified as a gibbon. So as you can see on the left, the panda was classified correctly with 57.7% or probability or confidence of the model. And then there is this noise that is added here. For now, you can imagine that this is a slight modification of individual pixels of the panda picture in a visually imperceptible way. And then you end up getting what you see on the right, which the model calls a gibbon. And if you know a panda and a gibbon is pretty similar to a panda, but it has also differences. But what is interesting here is that the model was 57.7% confident when it produced the right output, but you can see that it is almost 100% confident when it makes the mistakes. Here's another funny example where the magic of machine learning kind of manifests, right? So this image on the left is a tabby cat correctly classified with 88%. Again, with the same kind of perturbation that is added to the image, with the image still the same, it's really hard to visually differentiate the one on the left and the one on the right. But now it is classified to the wrong class, and this funny class, guacamole, with 100% confidence. Another funny example is where a pig is misclassified as an airliner. Again, this phenomena of being less confident on the right prediction and more confident on the wrong prediction keeps repeating itself. Here is one last example on the funny side where a school bus is misclassified as an ostrich. And again, the perturbation here is pretty comparable to the three examples I gave. Okay, so you might wonder, these are simple image classification tasks, and I may not be doing anything sensitive or anything consequential using this toy data sets. I would say, sure, but there are implications of this kind of perturbations on machine learning models that we can apply or that we use in very sensitive high-stakes applications. So in high-stakes applications, machine learning models are bound to be fooled by adversarial examples in adversarial or safety-critical environments. For example, you could apply machine learning models in facial recognition systems where you authenticate people, or you could use it, as I said earlier, in malware, intrusion detection, or in general cyber attack detection. You could use adversarial examples against voice-based assistants, spam filters, fraud detection in the financial sector, or even more in safety-critical environments where you use them in self-driving cars against models that power self-driving cars, or in the healthcare domain for doing all kinds of predictive tasks, including predictive diagnostics. Okay, so I'm hoping that by now you're convinced that this is way more than the funny examples that I showed you earlier. Okay, so to expand on the serious side of or implications of adversarial examples, I'll give you some representative examples of the possibilities of what adversarial examples can do. For example, going beyond pandas and pigs, right? So a spam detector, right? So a spam detector is a classic application of machine learning models where what you have on the left over here is a typical example of a spam that was correctly classified as a spam here. But by just changing some of the words, for example, the word start, just changing A with 4 and adding some benign or standard word here, you could fool the model, and then this is going to be misclassified as a ham or as a benign email. So the implication, the real life implication for this is the misclassification will result in spam emails, making it to inbox, and you would be bombarded by a lot of spam. Next, next use case where this might have serious implications is malware detection, right? So here's an example that was demonstrated with Android APKs. So without changing the actual binary of the Android code, by just modifying the Android manifest.xml file, which is basically modifying the metadata of the application, because that file stores the metadata of the Android app, the model that said this sample was malware with 90% confidence now flipped it in mind because simply the adversary just manipulated this. And the authors of this paper down here, they show that it is possible to achieve about 85% attack success by just manipulating the Android manifest file without touching anything sensitive in the Android model. Okay, so that was on malware. Here's another example where speech recognition could also be exploited by basically creating what we call audio adversarial examples. And the way this happens is the adversaries could exploit the inaudible frequency ranges that are not audible to human ear, but could be perceived or could be processed by this voice-based assistants, like the tools, the systems that we use in our homes, like Alexa and so on, right? So as you can see, this has implications. For example, if the voice, how are you, is perturbed in an inaudible manner to a human being, but audible to the device, and then that translates to this audio adversarial example, open the door. And if you're using this devices in a smart home where you could control them to open the door, or you could instruct them to open the door, this open the door could be induced as an instruction or as a command by an adversary. So it has safety implications. For example, if the door opens, the intruder would enter into your house. So the misrecognition has real life safety critical implications. In the text domain or natural language processing domain, you would see the same kinds of problems. So for instance, this is a text comprehension problem or classification where given a text, it's going to comprehend the text as a human would do and give you your answers. So the question, the answer to the question was this name written in green, but by simply adding this blue text over here, at the end of the text, the input text, this was misclassified as another person. So what is the implication of this? Because we're dealing with large language models, which ingest almost the text that we have on the entire internet and trying to do all kinds of generative tasks today. So the implication for this is basically if this miscomprehension happens, this could lead to misinformation where the wrong facts would be output to users, or it could also be disinformation where people could do intentional misrepresentation of facts on the ground. On another safety critical implication, here is an example of how people demonstrated as to traffic sign recognition going wrong in the sense of self-driving cars. So here, what you see is on these rows, these are different perturbations that they applied. And by the way, these are all physical attacks where this is not even done in the digital world. So they went outside buildings on the road and they used an actual self-driving car, model self-driving car that's used by research. And they tried to do this detection in real life, and the self-driving car was fooled almost 100% on this first row, as you can see, 73% on the second. In almost all of these cases, this stop signs were misclassified as the speed limit 45. So that you can see this is the implication of the misrecognition in this case is safety. The car could crash or people could die. Along the same line of self-driving cars, there are other functionalities like lane detection and object detection. Again, researchers have shown that it's possible to, for example, misguide a Tesla autopilot into onbound traffic to basically steer it in the wrong way and create safety implications. And again, what you see on the right is also a simulator that is going in the wrong direction, which is obviously safety critical. In the healthcare domain, machine learning models are used for diagnostic predictions. Again, the problem persists here as well. So what you see here is example of the model trying to classify different scans of, a retina of an eye, chest X-ray, and skin scans or skin images, and trying to predict whether the tumor is benign or not. And on this example here, the original image was classified as benign with almost 100% confidence. As you can see, the blue bar here is larger. But with the kind of perturbation I showed you earlier for the funny images, it now flipped into malignant, which basically implies misdiagnosis. And misdiagnosis, whether it is a false positive or a false negative, is going to be harmful anyway. So this has safety or security implications, as you can see. Okay, another example is facial recognition. So in facial recognition, you could use this for different reasons. One of the common applications is authentication. Another is law enforcement could use this for predicting, how criminal people are, and other similar. They could use it for other similar objectives. So the question then is, if perturbations like this, where for the image on the left, you just add this eyeglass filter, and you end up misclassifying the person not only to the wrong gender, but you could see that the target to which this person was classified, this person's face was classified, does not even wear glasses. So misrecognition in this case could lead to impersonation, or just bypassing a system that relies on facial recognition to authenticate users, or it could lead to more consequential situations, for example, wrongful arrest or indictment when used by law enforcement agencies like the police departments. And we have seen examples of this nature in the first lecture as to the consequences. And the last example I want to give you on the serious implications of adversarial examples is when this unmanned autonomous vehicles are used in the military operations, right? So in military operations, you have to rely on drones and the camera feeds coming from drones or this UAVs to take or to make decisions as to the military actions that you take. For example, you want to drop a bomb or you want to shoot a target, etc. So if a military, if such an autonomous vehicle that you use in military environments, for example, misrecognizes a school bus as a military convoy, right? Then you would, and you know that your target, travels in a military convoy. What you would do next would be maybe shooting that military convoy. But in reality, what you're shooting is a school bus. So civilians will be in danger in this scenarios. So as you can see, although I started with the funny examples, like a panda classified as a gibbon or a pig classified as an airliner, there are real life implications, and we have also seen enough examples as to the real life implications of adversarial examples. So in the more serious examples I gave you, you could see the diversity of the areas or the application domains where adversarial examples could be problems. Okay, so I hope that gave you also some sense of seriousness as to the the focus we have to have on adversarial examples. Okay, now, why do adversarial examples exist? What is really behind this phenomenon of adversarial examples, right? Unfortunately, we are still trying to figure this out. So there's no consensus yet as to, what is the conclusive cause of adversarial examples. But there's some hypothesis that is documented over the years, especially after the 2015 paper from Google that demonstrated this intriguing properties of adversarial examples, intriguing properties of neural networks when they are fed with adversarial examples. Okay. So I'll give you a bit of historical context as to the different hypotheses that people have put out, but this is by no means exhaustive, and hopefully in the future we'll get more answers. So back in 2015, when this paper kind of shed light on adversarial examples against neural networks, the explanation in that paper was somehow along the lines of this nonlinearity, the property of neural networks being nonlinear, and poor regularization. Then within a year, another follow-up paper looked at the same issue and tried to come up with this theory of the fact that neural networks are piecewise linear, which is true, because every individual neuron, as we saw, is a linear equation, and then you apply activation functions on top of that to add nonlinearity. And when you look at these activation functions like sigmoid, the value, and so on, you even realize that they are straight lines in the middle. So this was another theory, which, as you can see, is in contrast to the theory of nonlinearity. So this focuses on linearity, and the other one is about nonlinearity. So the two are opposite. And in 2016, another theory came, and this has to do with this notion of tilted boundary, where it says the model is not going to fit the data perfectly. So in this paper, they also provide empirical counter arguments against the previous two theories, linear or nonlinear properties of neural networks. In 2018, there was a theory or an explanation that goes well with the theory in 2016, which talks about lack of sufficient training data that would induce or imply the presence of adversarial examples. And then in 2018, this theory of building robust classifiers is computationally intractable. So we're going to be bounded by computational power. Therefore, there will always be some pockets of data distribution where adversarial examples are going to manifest. In 2019, another theory came, and this one has to do with the fact that adversarial examples are not bugs, but they're features. And this is because of the way classifiers are picking up non-robust features that would be very sensitive to adversarial perturbations, as opposed to robust features that would stay stable regardless of adversarial perturbations. And in 2022, we also looked into this problem in our lab. And one of the key observations that we make is the fact that most adversarial examples turn out to be out of distribution inputs. So that means once you apply perturbations and you try to see or position the adversarial examples with respect to the original data distribution of the model, the target model that you're trying to attack, it appears that roughly 75% of adversarial examples on image classification models like the MNIST dataset or the C510 dataset, they happen to be out of distribution. So our standing theory, at least in our lab, is maybe the adversarial examples are a manifestation, maybe a common manifestation of out of distribution, the broader out of distribution generalization problem we have with many machine learning models today. Okay, so with that, I kind of gave you a highlight of what the theory and the hypothesis has been around why adversarial examples exist. So roughly, I gave you a highlight of like a decade-long analysis of why they happen. But this analysis or this hypothesis is still ongoing. So we'll see what other people would come up with or what we can come up with as we look into this problem on a continuous basis. Okay, so that's on why adversarial examples exist. Okay, now the other interesting phenomenon that we observe with adversarial examples is this notion of transferability. So adversarial examples are pretty transferable. So if you craft adversarial examples, let's say for one class of models, suppose you did this for decision trees, and you try the same set of adversarial examples on another model, these adversarial examples, for the most part, are highly transferable to another model. And this is a study that we've made back in 2020, where we looked at multi-layer perceptron, which is sort of the kind of deep neural network that we discussed in the previous lecture, logistic regression, random forest, ensemble trees, decision trees, and so on. And we looked at the transferability of adversarial examples, for instance, taking the multi-layer perceptron as a source and logistic regression as a target model. All the examples, adversarial examples crafted for multi-layer perceptron, the 7% of those examples would transfer to logistic regression without doing anything. Of course, the transferability varies, but you also see, for example, as a target model, the multi-layer perceptron is it has a higher transferability from any of these models. For instance, if you start with logistic regression and you want to transfer this adversarial examples that you generated for logistic regression to multi-layer perceptron, you would end up with 86%. From random forest, 95% would transfer. So this is a very interesting phenomenon. And there are also papers that we have looked at into this problem of why is this happening? And again, there isn't a very conclusive theory on this, but there are some indications as to, for example, what features are being picked up, what correlations are being picked up when these machine learning models are trained. For instance, here, all these are variations of some tree representation. So they have this inherent similarity and the kind of features they will pick when they are trained. Therefore, an adversarial example that is fooling one would fool the other, right? So there are theories like this. And here's another evidence of the pervasiveness of transferability of adversarial examples across models. And this also kind of makes similar observations, even in a larger scale, because it looks at other models like support vector machine, k-nearest neighbor, and so on. Okay, so that was on why adversarial examples exist and this phenomenon of transferability of adversarial examples from one model to another, even if the models are architecturally different, as you saw in the previous two slides. Okay, so now let's talk about threat models and taxonomy, because adversarial examples are pretty relevant in security domains or security sensitive domains, right? Because the goal of the adversarial example is to fool the machine learning model. So the adversarial examples that we talked about, they show up in different forms depending on the goal of the adversary, what the adversary wants to achieve, what the adversary knows about the model and so on, and what the adversary can do or the capabilities of the adversary. So looking at the adversarial goal, we can broadly classify adversarial examples as untargeted and targeted. So in the case of adversarial examples that are untargeted, the goal is to result in misclassification to any label different from the true label. So basically what we're saying is if f of x is classified to some label y true, in the case of untargeted, when we generate x prime as x plus delta as the perturbation, we want to have f of x prime as y which is different from the original y true. So any y is acceptable as long as it's different from y true or the original ground truth label. For instance, in the case of the self-driving car, you could take a stop sign and misclassify, you perturb the stop sign and misclassify it as any other sign, because your adversarial goal in this case is, I don't want the self-driving car to stop at a stop sign, which has safety consequences. For the targeted case, the idea is you want misclassification to happen for a specific class or target label that you choose as an adversary. So basically what we're saying is we want f of x prime to be classified to y target, and we know y target is different from y true, and y target is picked by the adversary intentionally because that fulfills the adversarial goals. For instance, in spam, if you want to fool a spam filter or a spam classification model, you have to give it a spam and you want it to be misclassified as a ham because that would fulfill your objective. The same way for malware classification model, you want it to be misclassified as benign, or in facial recognition models where you want to impersonate a target person. So given your face, you want it to be misclassified as that other person's face, right? So these are the two broad classes of threat models of adversarial examples based on our adversarial goals. Then based on adversarial knowledge, we can put adversarial examples into three buckets: white box, black box, and gray box. In the case of white box, we are assuming that the adversary knows reasonable details of the model architecture, the parameters, some portion of the training data sometimes. In a black box case, we're assuming that the adversary has usually no knowledge or very little knowledge of the model architecture, the parameters, and the training data. In the gray box case, it's somewhere in between the two, but in general, we're talking about having partial knowledge about the model, its training data, etc. So these are the three broad classes of threat models based on what the adversary knows about the model, about the data, and other things around the data in the model. And then we have capabilities. A threat model wouldn't be complete without talking about adversarial capabilities. So in this case, we're talking about things like the capability to be able to craft adversarial inputs based on predictions and probability distributions, or collecting data and generating some auxiliary data from the wild. For instance, if the target model is an image classifier, then you can go on the internet and look for do web scraping and get more data that fits into the model's input dimension, right? Or you could query the model let's say repeatedly on this auxiliary data that you collected, and you could locally train a substitute or a surrogate model that you can use later on as a white box proxy to basically craft transferable adversarial examples that would tell you that, if the adversarial examples work on this local substitute model, then they would work on the target model because you trained the substitute model using the labels generated by the target model. Okay, so you used the target model as your labeling oracle, which basically speaks about the functional equivalence between the target and the substitute model. So these are the threat model considerations for adversarial examples. Okay, now to the important part of how do we craft adversarial examples. Okay, again, this is a very well-explored domain, and there are a lot of papers, a lot of techniques around how to craft adversarial examples based on the threat models that I shared with you. So if we have to cover everything, we won't be having enough time. So what I'm going to do is I'm going to show you some representative techniques and point you to the resources that you can explore more. So there's a whole range of methods, but the bottom line, as we said, for adversarial examples is given a function f, an input x, and a true label y, true, of x. If f classifies x as y true, now as an adversary, you want to produce x prime by adversarially perturbing x with this adversarial perturbation delta, such that f of x prime is misclassified as y, and depending on the threat model, targeted versus untargeted, this y could be any y different from y true, or this could be a specific class that you target. Okay, so that's generally the goal here. So at the end of the day, regardless of what technique I'm talking about, you end up with such a case where you produce x prime, the adversarial input, that would fall the classifier in a targeted or untargeted way. Okay. One of the popular adversarial example generation techniques is called fast gradient sign method. And in the sense of the threat model, this is a white box adversarial example generation technique. So the key idea is you have a model F, you have an input X, you know the details of the model. For example, you know the gradients, etc., how to compute the gradients of the input with respect to the model, the gradients of the loss function of the model with respect to the input, etc. Okay, so the idea is you want to perturb the input x in the direction of the sign of the gradient of the loss with respect to the input. And this perturbation is going to be controlled by what we call the perturbation budget. So you're going to scale the perturbation by the perturbation budget. You can't do the perturbation arbitrarily because, for example, in the case of images, if you do arbitrary perturbations, or if the perturbation budget is large, which means you're making a lot of drastic modifications, an image of a cat would look like something different, so that would be visually perceptible. So we have that constraint. So here is a formalization of the approach. So given x, the input x here, we have the function f, or the model f here, and we have the loss function j, and the gradient of the input with respect to the input x, and the true label of the input x. X prime is computed as x plus, so you're going to do the addition of the perturbation pixel-wise, okay? So imagine this is done element-wise or pixel-wise for a given image. So it's going to be the perturbation budget multiplied with the sign of the gradient of the loss function with respect to the input. And the reason why we are doing this perturbation in the direction of the sign of the gradient is exactly because the way machine learning models learn is through gradient descent. Now, if we want the machine learning model to make mistakes, we have to do the opposite of gradient descent, which is gradient ascent in the direction of the sign of the gradient. In gradient descent, we take the opposite of the sign of the gradient. In this case, we follow the sign of the gradient because we want the model to make mistakes with respect to the current input. That's the basic idea behind this fast gradient sign method. And as you can see, it is a one-step perturbation, and that's why it's called fast gradient sign method. And you can very quickly generate thousands of adversarial inputs by using this technique. The other popular adversarial example generation technique is called projected gradient descent, or PGD for short. And this is, again, white box. Okay, so this technique is built upon the fast gradient sign method, but the way we're going to do the perturbations is in multiple steps, basically taking baby steps to make sure that, just like when we do the learning rate, the values of the learning, when we pick the values of the learning rate in gradient descent, if you pick a big value, we might, in one step, jump to the wrong place in the loss landscape. The idea here is also pretty similar. For the fast gradient sign method, although it's a method that you can use to generate an adversarial example in one shot, there is a probability that, it's very likely that you might overshoot and get the land on the wrong spot, right? So it may not work all the time. The adversarial example that you generate may not always fool the model. I'm not saying everything you generate in projected gradient descent is going to fool the model, but it's going to be much better than the fast gradient sign method, simply because we are incrementally exploring or perturbing the input so that we can query the model and see whether we can fool it or not, right? So we can avoid this overshooting in the case of, that is possible in the case of fast gradient sign method. Okay, so the idea is pretty similar. You add perturbation to the input. And since this is an iterative process, you have to take some number of steps, right? So you're going to set the initial input, the initial adversarial input as x0, which is the input itself at the starting point. And you're going to choose this small positive step size, which is semantically similar to the learning rate, a parameter that we have in gradient descent. And then you have to choose the number of steps. And again, the number of steps could make this slow or fast, depending on what you pick. But in general, at stage I of the process, what you're going to do is you are going to apply a clipping on what you compute. And I'll come back to what the clipping is doing. So given the adversarial example that you generated in the previous step, step I minus 1, you're going to do the same thing. So what is right here is exactly what we did in fast gradient sign method, okay? Except that we replaced the alpha here for epsilon, but there is epsilon over here, and I'm going to talk about that as well. So everything else is the same. So the loss function, the gradient of the loss function with respect to the input at step I minus 1, and multiplying that with the step size, and then adding the whole perturbation to the previous input, and then clipping it with respect to the perturbation budget. So the perturbation budget is to make sure that given an input x, let's say x is right here, the perturbation budget is going to be a ball around this where the radius is epsilon, okay? So we want to make sure that when by doing this clipping, we want to make sure that if the x prime steps outside here, we want to bring it back here by doing the clipping, okay? So you apply the clip of x prime and bring it down, bring it back to the LP ball, the so-called LP ball for the neighborhood of the input, okay? So that's basically how the adversarial example generation happens in the projected gradient descent technique, which is another white box adversarial example generation approach. Okay, so in the space of adversarial example generation, there is a whole bunch of techniques, and I can't be exhaustive about those, but I'll just highlight some of them. For example, deep Foley is one of them. Carlini-Wagner is another white box adversarial example generation technique, which happens to be very powerful, but it also is super slow to compute because it basically iterates or tries to explore until it finds the right perturbation that fits the model. We have also looked at adversarial example generation using or leveraging explanation methods, machine learning explainability, where we boost the effectiveness of this techniques like FGSM, PGD, and Carlini-Wagner, and so on, to make the crafting of adversarial examples smarter or more accurate. And there are also physical attacks, like the traffic sign physical attacks I showed you earlier, and also a whole bunch of black box attacks that are used to full machine learning models using adversarial examples. So the bottom line here is, as I said earlier, the basic idea behind adversarial example generation is the same. Given an input and a function and some knowledge of some adversarial knowledge, whether it's black box or white box, you want to end up with x prime which is X plus the perturbation delta. Okay, now let's talk about, okay, so that's sort of a highlight and an example of adversarial example generation techniques. So we have to also talk a little bit about defense against adversarial examples to make sure that the picture is complete here. So just like the attacks, a lot of defenses have been proposed, but most of them are broken. And as we speak, there isn't like an outright, best defense that we can pick, but this remains work in progress. So this is a slide from Ian Goodfellow, who was the guy who introduced the fast gradient sign method and other follow-up techniques around adversarial examples. So this slide basically summarizes all the techniques that have been tried as defenses against adversarial examples and eventually failed. So I wouldn't be wasting your time talking about failed defenses. I'll rather focus on some defenses that are not perfect, but give some reasonable robustness. And one of them is called adversarial training. So adversarial training, the key idea in adversarial training is you basically introduce the model to adversarial examples so that when it sees adversarial examples in deployment, it will say, oh, I know this adversarial example. You're planning to fool me. I know the right class that this input should go to, so I'm not going to be fooled by you, right? So that's basically the idea behind adversarial training. And the advantage is that it reduces attack effectiveness by a reasonable margin. And the downside is it doesn't come for free. So the robustness gain that you gain, it doesn't come for free. It penalizes clean input accuracy or benign accuracy. So the algorithm you see on the right roughly captures what adversarial training is going to do. We just do the usual stochastic gradient descent training regimen, but you introduce the notion of, okay, training on adversarial examples. So for each epoch, for each mini batch, you're going to do the following. So you're going to compute gradient loss with respect to the weights. So as you do it in the standard gradient descent, and you compute the original gradient with respect to the weights of the model, and you update your weights or parameters. And this part is the standard SGD. And then you're going to generate adversarial examples with the current version of the model you trained up to that point. For example, you use FGSM. If you use FGSM, that is the formulation of the adversarial example generation. And you compute the loss on the adversarial examples that you just generated. And you compute the adversarial gradient, and you update the model parameters. You take the W that you have up to that point, and you update it down here with the gradient adversarial, right? So with respect to comparing this with the original, what you're doing here is exactly SGD, but the SGD that is happening here is SGD with adversarial examples. So by repeatedly doing this for as many epochs as you have, the hope is that the model would familiarize itself with adversarial inputs. And the next time it sees a familiar example generated, let's say, through this FGSAM attack, it would say, okay, I know this is an adversarial example that is trying to fool me, so I won't be fooled. So that's sort of the basic idea and story behind adversarial training. Adversarial training, as I said, comes with a cost. And back in 2021, we also looked at adversarial training and how much accuracy gain we can get, or robustness gain we can get by doing adversarial training. So the model, the undefended model, is 99% accurate. This is MNIST, the image classification model. And when we adversarially train it, you end up with more or less the same kind of model in terms of accuracy, so we don't lose much. But when we look at the attack, so FGSM, for instance, if you use the kind of attack I was talking about earlier, the undefended model drops down to almost 10%. And with adversarial training, it it gains about 32% accuracy. And this varies from attack to attack. For example, the Carlini-Wagner attack is a very strong white box attack, so it simply paralyzes the model, and it doesn't recover even if you do adversarial training. And we also tried with other attacks like SPSA, which is one of the black box attacks. The undefended model goes to 30%, and then through adversarial training, it comes back to almost 60%. And we also do try this with a combination of a model extraction. So the copycat attack here is a model extraction combined with white box adversarial example generation attacks. And we see the value of adversarial training in gaining a robustness to by some margin, okay? So that was on adversarial training, right? Another class of defenses that is promising, but still work in progress, is this certified robustness defense. So certified robustness is, the key idea here is you want to guarantee to the user of the model that regardless of how much perturbation happens on the input, I'm going to give you the lower bound of the accuracy that you would gain out of the model, despite what the adversary is trying to do. So basically what we're saying is the model's prediction remains unchanged with what we call the epsilon neighborhood of the input, right? So you have the input over here, let's call it X, and there is your epsilon, and you just draw a ball around it. And if adversarial examples appear within this LP ball, then we can formally guarantee that the model's accuracy won't drop below some percentage, for instance, okay? So that's a very promising idea, but we still have to see this used in like large, complicated models and so on. Another class of defense that is promising is this notion of moving target. So making the model a moving target in the eyes of the adversary. So the way this is going to happen is you're going to create a model pool where each model is more or less the same, except that there is slight variation in the decision boundary of the model. So the idea is you want to basically reverse fool the adversary so that the adversary will perceive this as one model, but internally the model is just changing. So this different model, for example, in this case, there are 6 models here. The 6 models will take turns to respond to the query the adversary is sending. So at one point you get this model, at another point you give it another model. So the prediction API keeps dancing around these different models, which are slightly different in terms of their decision boundary. And eventually the adversary will not have a pattern of what the model behavior looks like, because every time the adversary comes back, the input, the model changes. So this is work that we have done on top of adversarial training back in 2021, and we call it morphens. So the system is called morphens. So basically a model that morphs every time the inputs, the adversary sends an input. So the idea is pretty simple. So you start with a base model, let's call it FB. We train it on some training data, and then we perturb the weights or the parameters of this model and create copies of this model. And the copies of this model, because the weights are perturbed, may be less accurate. So we use some data augmentation techniques to retrain these copies and gain back accuracy, and also introduce some sufficient diversity between the models to avoid transferability. And once we have that, we have this n number of models. And then what we do next is the interesting part. We train a subset of these models using adversarial training. Okay, the technique I just described. And we leave the remaining subsets as they are, so that we have a diversity of models that are more accurate on clean data and models that are more accurate, naturally more accurate on adversarial data. And when we get inputs, we also have this scheduling and renewal part of the model pool, because this model pool should be renewed every, let's say, when the maximum number of queries is reached, because we don't want the adversary to figure this out. And every time an input comes in, we have this detector that intercepts the input and checks whether it's outside the distribution of the training data. If it is, it will send it, it's most likely an adversarial example, and it will send it to the adversarially trained model because adversarial examples are, for the most part, out of distribution as per our observation that I shared with you earlier. Otherwise, the inputs would go to the models that are more precise on clean data. So we compared morphins with adversarial training, and here is a comparison. So the gray bar is morphins. So what you see here is morphins, and the orange bar is adversarial training against fast gradient sign method, Carlini, Wagner, and SPSA attacks. And as you can see, overall, morphins outperforms adversarial training when you look at the accuracy under attack. So that is one contribution that we've made in the space of defending adversarial examples using moving target defense ideas, and our technique outperforms adversarial training, which is one of the reasonably, reasonably well-performing defense techniques that we know today. Okay, so I'm going to end this lecture with this notion of distribution shift, connection of adversarial examples with distribution shift. So the broader problem with adversarial examples, it usually traces back to the fact that these adversarial examples are outside the distribution. And this is traced back to the way we train machine learning models today, which is essentially based on the IID assumption, right? The IID assumption, where we believe that test data or inputs come from the same distribution as the training inputs. So as you can see, what you have here is we train the self-driving car on inputs like this, where the stop sign is very clean or clear. But when we deploy the self-driving car, the stop sign might be covered by, let's say, a tree, right? So we have to take into account this kind of real-life situations. And this notion of distribution shift is applicable in many domains, including in medical domains, where, for example, you take MRI scans with medical imaging devices, where different hospitals would have different data, and that results in selection bias, pre-processing variations, etc. Okay, so out of distribution generalization is a very important problem because real-life test inputs may come from distributions that are not that do not really conform to the training distribution of our data. So the idea is, or the solution is, to aim for out-of-distribution generalization. This is also a very emerging area, and we have a long way to go to figure out things, but there are some techniques that stand out. For instance, invariant risk minimization, where you want to train the model so that it picks up features or it picks up correlations that are invariant to or insensitive to perturbations. The other is what we call risk extrapolation. Risk extrapolation, the idea is, for example, over here is the boundary of what the data distribution covers, right? The yellow triangle here. So you're going to extrapolate risk and try to introduce or test the model with respect to data distribution shifts, right? So basically, robustness to larger data distribution shifts. These are just some of the highlights of the directions we're taking in the sense of data distribution, out of distribution generalization. But as I said, this is also an emerging area. Okay, so finally, what we covered in this lecture is basically, we talked about adversarial examples, what they are, what their implications in real life is, and why they happen. We talked about the threat models, white box, black box, and gray box. We talked about the goals based on adversarial goals. They could be untargeted or targeted. We talked about how we can craft adversarial examples. We talked about some of the noteworthy defenses and where we stand in the defense landscape. And we just highlighted the importance of paying attention to distribution shift and looking for techniques that would do out of distribution generalization. Maybe that is the direction we have to take to take care of, or to kind of have a good handle on adversarial examples. Okay, so that we conclude the lecture for today, and I hope to see you for the next lecture.